All right, good people. Video number two of this hodgepodge of ideas that we have left over. This actually came up in the video about the squeeze theorem, which itself was one of those topics that you need to know, and yet it doesn't come up often um, in calculus class or on the AP exam. But it's a big enough idea, and one of the reasons we bring up the squeeze theorem is to prove these two limits, which were also in that video that I made for the squeeze theorem. The idea here is that you just need to know these two. Are they going to appear on the exam? We don't know. We haven't really seen them that often, but you never know when they can pop up on a multiple choice, and that would be an easy point to get. So we're talking about the limit of sine theta over theta, or sine x over x, so the sine of something over something, as long as these two somethings are the same, as though somethings go to zero, as the theta goes to zero, as the x go to zero, my limit is always 1. We need to always remember that whenever I see this pattern, my limit is 1. I also need to remember that the limit of 1 minus cosine theta over theta, or 1 minus cosine x over x, or 1 minus cosine of something over something, as that something goes to zero, is equal to 0. So these two we just need to know. How do they appear? Well, here's one way they could appear. They could appear in terms of some variations of those two. Now, the first example, not really a variation, because if you think about it, we're looking at the limit of the sine of something over the same something, which is what this limit in the box is telling you, right? We don't know what theta is. Theta could be anything. So what if theta was 5x? Then the sine of 5x over 5x as x approaches 0 is automatically 1. So this doesn't look like the box, but it follows the pattern of the box, meaning that I have this inside of the sine function and this denominator the same, and that they're both going to 0 as x approaches. Not that they're both going to 0, that the x is approaching 0. This thing that I circled in blue is approaching 0. Because that's what's supposed to happen, right? Sine of something over something as the whole something approaches 0. Sine of 5x over 5x as x approaches 0, well, that's going to take this to 0, and that's going to take this to 0, meaning that I have this situation, and I can guarantee that the answer is 1. If you want to use your calculator to graph that and look at what's happening near x equals 0, you'll find that the limit is going towards 1. But the second example is slightly different. And so I want to show you the mathematics behind it, and then we'll see if we can pick up a shortcut. So I'm going to zoom in a little bit. I don't have the same thing I had before, the sine of something, but it's not the same something. So I'll do a different shape. Not the same something, right? So what if I rewrite this and I say, well, if that 4 wasn't there and it was a 5, then I would have that limit, right? So I'm going to scoot, since I'm multiplying 4 times x, I'm going to scoot that 4 to the front. And this pen is awesome. It's awful. I'm going to scoot it to the front. I can do that because if you think of multiplication of fractions, how do we multiply fractions? Well, you multiply the numerators, 1 times sine 5x, we get the top. Multiply the denominators, 4 times x, you get the bottom, right? So nothing's changed. But at this point, what we really want is for this to be 5, because then I would have that, right? But what if I introduce that multiplication of 5 in the denominator, and I can do that if I introduce a multiplication of 5 in the numerator, right? As long as I keep it balanced, it's still the same. So far, so good. Okay. Well, what if, and I can, just like I pulled this 4 because I was multiplying, I pulled it to the front. What if I pull this 5 to the front? And then it becomes 5/4 times the sine of 5x over 5x. I'm sorry, it's bothering me. This is pretty terrible. Sine of 5x, excuse me, over 5x. Now I have the situation that I want, because now sine of something over something as x approaches 0. But this is where I can use those properties that we talked in video 1. One of the properties said if you're multiplying by a constant, you can pull the constant out of the way, take the limit of the function, and then multiply it back in. So the rule says I can take this, the property says I can take the 5/4, hold it while I take the limit of this. And I can do that because the 5/4 doesn't have an x, right? This doesn't have an x. The limit is affecting x's. This doesn't have an x. So I can pull it out of the way and it'll be fine. Excuse me. Now, when I look at this, well, we said on the first example that that equals 1. So therefore, this equals 5/4 times 1, which is just 5/4. And that's my answer. That's the mathematical way of showing that that's the case. Is there a shortcut? Do you see a shortcut that we could have used to get from the original limit to my answer without doing all the mathematics in the background? Do you? If so, what do you think the limit as x approaches 0 of sine pi x over 2x is? If you think you see a pattern, what do you think this would be? I can't use that special limit because when I look at the inside of the sign and the denominator, they're not the same, right? But do you think you can predict what it is? The answer turns out to be pi over 2. That would be the answer. Do you see the pattern now? I hope you do. Use that pattern. Again, whenever I have the sign of something over something else, and the only difference is the numbers should be the same, not when I have 4x cubed, not when I have other things, but when I have just sign of something over something, and the only difference between the somethings is that it's a different number, then I can focus on the coefficients, and that will be my limit. Maybe a shortcut you can use. I'm going to skip to the last example, and then I'll come back to the next to the last example. How do I take the limit of 2x plus sine x over x as x approaches 0? Any ideas? If you have an idea, pause and kind of play with it. If you don't have an idea, I'll remind you, whenever we're dividing by one term, I can divide each of the terms in the numerator by that one term. So I can say we're taking the limit as x approaches 0 of 2x over x plus sine x over x. Because I have two things that I'm adding, but I'm dividing everything by the same thing, the x in the denominator, I can take the first thing divided by x, take the second thing divided by x, and then add them together. Oh, but the property of limits says I can take the limit of this and take the limit of the second part, or the second function, and then add those together. Well, the second part is 1 plus, what is this? What can I do with this expression? I can simplify the x's, and then I'm left with 2. So therefore, my final answer is 3. I'm using the special trig limit. I need to remember this, right? But I'm using it as a way to solve or evaluate limits that might otherwise look a little bit, but if I break it up into little pieces, it comes in to help us out. And then finally, we'll look at this example. Any ideas? I don't know. There's a lot going on here. First of all, do you notice that there's a constant? So I'm going to pull that constant out of the limit because that constant doesn't have an x. It's not going to be affected by the limit. So I'm just going to write it in the front. 5 times the limit as x approaches 0. Now here, I'm going to separate my numerator and denominator. And I can do that if I write it this way, times sine of 2x over 1. Remember how we multiply fractions. You multiply straight across, numerator times numerator, multiply straight on the across on the bottom, denominator times denominator. That would get me back to where I was, right? Is this the limit, the special limit we need to see, the special pattern in order to do it? Well, no, it's missing something here, and this one's missing something there. So what if I multiply the one that I just erased? What if I multiply the one by x? Let me do it in a different color so you can see that it's going to pop up here. But if I do it on the denominator, I'm going to multiply the top by x. So if I multiply 1 times x, I'm going to get x. I'm closer. Oh, and now I can see that I can separate these. I'm still going to put the 5 there. Remember the property of limits that says if each of these limits exist, then I can separate them into this times this. What did we say was a shortcut to figure this out? Don't we just look at the coefficients? So therefore this would be 2. And then can I do the same thing with this limit? I just look at the coefficients. Let me do it in blue. I just look at the coefficients, and that's my answer. But don't forget, we had another constant, the 5, that was going along for the ride, and that is going to be our answer. Whatever we get, we multiply 5 times 1/3 times 2. That's our answer. And when you multiply 5 times 2, you get 10. And 10 times 1/3, you get 10/3. That's your answer right there. So the moral of the story is, if you remember these two special trig limits, they can help you break some complicated looking limits down and figure out the limit value fairly quickly.